Good afternoon, everyone. Good afternoon. Welcome again to our virtual pre-lab lecture. Today is our last meeting. This is the last lab you are going to do this semester. Let me take this early opportunity to thank everyone for giving me the opportunity to be your instructor this summer. If I don't get to see you, I want to wish you all the best in your careers. One thing I did miss is interacting personally with you in face-to-face instruction. Nevertheless, I do understand the situation. We have to make the best out of it. Because of time factor, I will not I will not assign you any more quiz. The quizzes you have done so far is enough because there is a short amount of time you need to complete tonight's or this afternoon or experiment. If you haven't checked the due date for this lab, it is I put it to be this coming Friday because next week you will get your grades by next week, same time. All the grades will be posted and it should reflect on your transcript. So that's why I'm just kind of like pushing the due date to this Friday. And with that, you will not do a quiz on precipitation, the electrochemistry. All the only quizzes posted, all right, there will be no more quizzes, only the quizzes which have been posted. You should complete them before Friday. If you have any difficulty, please, or any situation, any concern, please kindly send me an email and I'll respond. So today is our last meeting, and Friday, I expect you to turn in to today's data sheet, all right, including if I made a mistake on the post lab, maybe I put it Sunday or this coming weekend, please try your best to get out of your way, all right? Other than that, next Wednesday, it will be too late because I believe Tuesday, I need to put in your grade, so I need to be on overdrive on grading your work. All right, let's shift gears to our experiment. It's a dry lab. I'm just gonna share my screen here because of some notes I'll be making on my whiteboard. I'm gonna be making notes on my whiteboard, and please have a pen and a pencil somewhere. Let me ask you this: have you, if you are taking the course right now, or if you took the course before previously, please use the chat box and let me know if you have covered, if you covered the concept or the chapter on electrochemistry. It's just going to help me a lot if I will get to know if you have, yes, you have covered. So I don't want to preach to the choir that you already know the material. That's my expectation. And that is all about the ATA experiment. The labs were designed in such a way that when we do the experiment, you should have covered in the lecture. So that's the same thing with this lab. So I know you know some of the material. What I'll just do is just kind of like real quick wrap up and explain how things are and see if you are and give you material or information which are enough for you to complete the data sheet available online. Well, electrochemistry is basically the study of chemical reaction which generate electricity. And what is electricity? The flow of electron from point A to point B, right? Electrochemistry is the study of chemical reaction which generate electricity. In generation of electricity, we use a cell, and there are two types of cell. You should distinguish and know how they operate. There is what we call galvanic cell, all right? And there is what we call electrolytic cell. Galvanic cell you see here uses spontaneous chemical reaction. You know what spontaneous is? A spontaneous reaction is a reaction which, once it gets started, all right, it will never stop, all right? It will continue on its own. What you see here on the corner of my note here, or not really a PowerPoint slide, but the right side of the screen. This is an example of galvanic cell. I'll not get into the electrolytic, which uses an external source of power to generate electricity or make the electrons move from point A to point B. Oh, well, it's a nice diagram. You can just look at it, but there is more than just looking at it and just, just like any other diagram in your text, this diagram here, you should be able to do the anatomy of it. What I mean by anatomy is knowing which one is the anode, which one is the cathode, which one is the, or what is a solar bridge, what's the purpose of the solar bridge, what is an electrode, or what is an electrolyte, what should go where will the electron flow, and so forth. Well, it doesn't really matter how you construct, all right, you construct the galvanic cell. Over the years, I've learned to construct my galvanic cell in such a way that my galvanic cell consists of two cells with two reactions taking place on the two compartments of the cell. There is what we call the anode, all right? How you label that, the anode and the cathode on this side, you notice that there is a porous material. Some texts mention that as a porous material. This is called the salt bridge. And this is just to facilitate the flow of electrolyte or ions from one point of the cell to the other point. We got here the electrolyte. We can have electrolytes, different solution here. All right, and we have electrodes. Electrodes, it's just like a metal, and we can have an electrode here. An electrode is selected in such a way that the solution is made up of, the solution here is made up of ions from the electrode. For example, if this is copper, this could be copper 2 sulfate solution. If this is zinc, maybe this is zinc sulfate solution, and so forth. Now, here is the voltmeter to measure the voltage. It will be 0.474, and there is a wire here, like a wire to facilitate flow of electrons. What you see, this one, if I look at the diagram here, it shows flow of electron from this end to that end. For mine, I will have this R, which indicates the flow of electrons to generate electricity. So electrons are moving from anode to cathode. You have to know the rule of thumb. Where are the electrons flowing? And that is what I was saying. You got to understand the anatomy of the galvanic cell, how to construct the galvanic cell. Well, how do I know which one is which? Can we flip over the equation? No. In galvanic cell, all right, in galvanic cell, the electrons flow from anode to cathode. That means we are losing electrons. We are losing electron on this side. And we are gaining electron on the cathode side. When you assign, remember, it's got to do electron, right? From the previous chemistry course you took, electrons are negatively charged. So we assign this as negative. This is negative terminal, and this is positive terminal, where is positive, negative. How do I know that? How do I assign those terms? Because I know electrons are negatively charged and electrons are negatively charged. So this end has high electron potential. So if you have, just think of water. Water flow from high, all right, high altitude to low altitude, like it's just gonna flow. The water will not flow from, down the stream, up the stream, but up the stream, down the, so configure that too, that electrons will flow from high. So we have high electron density. We may use that analogy that this anode, high electron density, low electron density. So it's gonna flow from here. And if there's a light above here, we will see it lighting. If there's a voltmeter, we will see some voltage reading here. And that is how the soul bridge works. Now, this solution is selected in such a way that I'm just going to give you an example. This could be zinc. This is zinc electrode. This is zinc metal solid. And then this is zinc sulfate solution. This is aqueous. It's a solution in that. And this is right here is copper 2 sulfate solution, and here is the copper. Here is the copper electron. This is solid. Since electrons are being, and here you may have an electrolyte, strong electrolyte, could be potassium nitrate, and potassium chloride. We're not gonna get in details to that. Over time, we will lose the metal right here. The metal will be eaten away. That it will just, over time, this is what's gonna happen. You're just gonna have like a small, that the electrode will be eaten away. It will just go into the solution. And with time, the electrodes on this side will just get bigger and bigger. Like there will be some reduction. Here, when you write the half cell potential for this, zinc, this is oxidation, solid, going to zinc plus 2 electrons. We are losing 2 electrons. Here, there is a reduction of copper, Cu plus 2 electrons to go to copper solid. On the anode side, we are losing electron. On the cathode side, we are, cathode side, we are gaining electron. This is where oxidation takes place. And this is where the reduction takes place. Reduction. That means we are reducing copper ions. What is written next to, this is potassium chloride. Don't worry about that, Cynthia. This is, I was just putting potassium chloride. This is to balance the ion. Let me just break that. In case of you're wondering why this is, maybe it's gonna help you in the exam. It's gonna produce potassium and nitrate. If we are losing electrons here going this way, we need to bring nitrate on this side to balance the charges. If we are cutting away copper of the solution of this, we need to replace the positive. So potassium will go on that side to balance the charges. So it's just potassium to provide more more charges. Since we are losing negative electron here, the negative ion in the soul bridge will move this direction, and it goes that direction. I hope that makes clear. Cynthia, did I answer your question? That is potassium chloride here, KCl. That is a stroke. It's just a
so the K plus is going to the cathode, or no, the anode, and then the
I can't hear you. Let me just say, I don't know why your microphone is so low. Are you talking to me, Cynthia?
So can you hear me?
You said what?
Can you hear me?
Yeah, I can hear you.
Okay. I'm sorry, I'm on my phone doing this. So the K plus, is that going to the anode, and then the nitrate
The
or
K plus
nitrite is
here,
going
right?
to the,
Yeah,
yeah.
you know, this in the solution we will have C minus and K positive from potassium chloride. Since you are removing copper ion here on the solution to coat or to plate the electrode here, you see the plating right here because we are losing copper 2 positive or ion, and therefore we need to replace those for the cell to continuously work to allow the continuous, otherwise the cell will collapse. So potassium will flow in this direction, positive. And then since we are losing electrons on this side, which are negatively charged, any negatively charged anions or on this solvent here will migrate on this side. Yes.
Okay, thank you.
Does that make sense?
Yes, it does.
Yes, yes. So you need to know, sometimes they might ask you in the exam that where will the, potassium or whatever, or what happened to potassium in the solvent, where will they go there? We are losing cation on this side and we need to replace, we are reducing. We are losing electron on this side, it's moving on that side, we are losing that and we need to replace that as, well, electrons are flowing. It's gonna be like that. So having said that, this construction here from the diagram, all right, from the diagram, you can relate to, let's see if this one gives you, this, it doesn't give you which one is which, but I'm just giving you complete detail how you construct. Sometimes they may give you like label, what is it? There's a diagram you need also to relate to this. We can write this as a diagram that think solid plus, all right, copper 2, before when we write a complete equation, we have half reaction, whatever is taking place on the anode, we call this half reaction oxidation, half reaction reduction reaction. So we will write this as zinc. All right, here is, this is zinc solid going to zinc 2 positive, and this is aqueous plus 2 electrons. This is anode, and this is cathode. Zinc copper 2 plus 2 electrons. Since it is 2 electrons are lost and 2 electrons are gained, we don't need to balance. If it's not balanced, you need to balance the equation. You need to balance the equation. This is solid right here. Solid. And the overall equation will be like this. Zinc, all right, zinc solid plus copper 2 positive aqueous going to copper solid plus zinc aqueous. This is 2 positive. This is overall equation. This is overall equation. But whatever is happening here, this is for the half cell reaction, half cell reaction. Now, real quick, I will jump into determining. You see this voltameter right here? It reads the voltage. If we complete the, the cell by immersing the cell bridge to provide the ions, we will be able to see the voltage reading for our galvanic cell, depending on the concentration of electrolytes, experimentally. We can also determine what we call the cell potential, standard cell potential. You know this equation, E cathode minus what? Minus E anode. You know, remember this equation? Do you remember this equation? Yes, you need to know. Once I know that, and remember this is a standard. You know what means a standard, right? That means the concentration is, 1 molar, maybe temperature. This is the concentration. Temperature at standard state, 298 using Kelvin, all right? 298 or 25 degrees Celsius, and pressure is always 1 atm, 1 atmospheres. If we are just a condition to this, we are talking about, the standard cell potential, In order to calculate, the standard cell potential for any galvanic cell, you need to identify which one is the cathode, which one is the anode, which one is the cathode, which one is the anode. Once you identify that, and then we just plug it in the equation. I posted the standard reduction potential online. I'll show you where they are. Online, I do have the standard cell potential, half cell potential of half reaction. Let me just pull that real quick and show you how you read, because you may have it, but you don't know how to read them. You should be able to read the standard. I do have online, but I don't know if it's gonna play on your end. If not, please send me an email. I had to embed online, all right? This is the standard cell potential. If it doesn't play on Adobe Flash, just click that, and these are the standard cell potential. Remember what I said earlier on, that electron flow from high to low. So if something is above, then we know that is an anode. If something is below, then we know that is a cathode. Because at the top right here, that means it has high potential. Forget about, the science right here. There are two methods of reading the standard cell potential or using that potential we talked about. If I look at zinc, it is, zinc is above copper. That's how you read this table. Zinc is above what? Copper, which means electron will flow from high to low. Just think about it. This is what I normally use, and it works all the time. That electron will flow from something above it to something below. It cannot be the other way around, that electron will flow from copper to zinc. That's how you can assign anode and cathode. So if I know that electron will flow from zinc, which is above copper in that case, right away I know my cathode, I know my anode. I know my cathode and I know my anode. So if I plug it in the equation, all right, if I plug it in the equation, I'm gonna pull in a minute, my anode, which is now negatively charged, will be what? Will be right here, anode 0. What? Cathode. Where is cathode? Right here. Copper. They're using 0.16. No, copper 2 right here, not copper 1. Make sure you read it while I was trying to write this, but this is the right one for 2 electrons. So 0. This is what I'll say, 0. To show you how to find the standard state. Right here, it's gonna be 0.3 4 minus 1, no, 0.76. 0.76. fold. Let me just minimize this and go back to our, you see this, our equation. You may use, or your instructor may have used a different approach, but I do find this one, you know, working well. I know somebody might have told you, oh, you got to flip the equation, and you know, that's too much. All I have to know is which one is my anode, which one is my cathode, and then I just plug it in the equation. All right, and this will be 0.11, right? Force. That's how you find this standard. All right, the standard cell potential anode minus cathode, anode minus cathode, using that. If we are to use that cell potential, then construct a galvanic cell at standard state, then we will use that. We will use these to calculate. Experimentally, we have just to construct a cell, and then we record the what? Record the voltage, record the voltage. At non-standard state, all right? At non-standard state, before I show you non-standard state, the cell could also be constructed in such a way that at non-standard state, we'll see that in a minute, how to construct the cell. If we construct the cell sink, what I'm drawing here is just the diagram of a galvanic cell, the diagram for galvanic cell. And what is a single vertical line in a galvanic cell diagram right here? What does this represent, if you remember? It represents what? The whole of it, Cynthia, this is anode right here, but I'm talking about this vertical line right here. Yeah, the whole of it is, this is the anode. You got this part right here. The whole of this is anode. The whole of this is cathode. But what does this vertical line represent? What does these two vertical lines represent? No. To save time, this represents what we call phase boundary. You may remember that. That means when I dip that electrode in there, there was a solid and there was a solution. I'm dipping the zinc electrode in the zinc sulfate solution. So this represents the phase boundary between the electrode, which is solid, and the solution. And this represents soul bridge. If you forget, right here, this is called the soul bridge. To save you, they might ask you in the exam that what does two vertical line represent? What is a single vertical line represent? This represents phase boundary between the electrode, which is solid, and the solution. Remember, when we dip that, you're gonna see that later on. So right here is the Calvan diagram, or equation for galvanic cell and what it represents in general without doing that. And of course, this is the anode, and this is the cathode. This is the cathode, just to give you an idea of that. All right. With that, there is an equation. If we are working in the lab, the pressure could be, if we are working in the lab, the pressure could be different from 1 atmosphere. It is 1 atmosphere is 760 millimeter mercury. Maybe it is 765 millimeter mercury or less than that. Pressure varies from time to time. And how do we determine the cell? All right, the E cell at non-standard state, we use the Nast equation. This stands for cell potential at non-standard what? Non-standard state. That means the temperature is, like today the temperature is higher than 25. It could be maybe 28. All right. It could be higher than that. And how do we determine the cell potential? How do you determine the cell potential? We use what we call Nast equation, all right? We use Nast equation at non-standard state. We're not going to look at the, the equation for, finding the galvanic cell. You're not going to use that equation to find in the lab. How does Nast equation look like? We use at non-standard state, we use Nast equation. Nast equation. I mean, somebody's here. Let somebody in. We use Nast equation at non-standard state. So if they ask you use Nast equation, how will you find the Nast equation? It is, all right. It is given by E of cell. This is Nast equation. Cell. Note that I didn't put the superscript. You have to use the standard cell potential to find this using the previous equation. Yeah, you got it. Thank you. Thank you, Cynthia. And this is reaction quotient. You know what it means. So that means this reaction quotient is the concentration of this ion and concentration of this one, and a product of a reagent. You know what it means. So I don't want to spend time on that. You know the Nast equation. That explains, the other part. We're not going to look at that. Let me just fast forward to the experiment. How are you going to do that? This is the data sheet, and there's some simulation. You're gonna find out that I haven't gone through the experiment. You will. This is the cell I constructed. Now this is the anode. This is the cathode, and you have to construct that from the demonstration here. All right. From the demonstration here, you should be able to construct that cell. Now once you go back, if this one doesn't run, if you encounter any problem with Adobe Flash, I know they are moving, they are retiring it. What I did is I embedded on Canvas, which if you go through Canvas, you may be able to play it. But right now, if you try this, you may end up with let's try and see. It might allow me, it might not. It depends on, it will allow me, but in case, because I know some folks do not get this, and then you will have to start, go through Canvas to assess that. So here is just a simulation on how if the reaction just trying so back and forth, that if you put in that, will the reaction take place? That means this is an aqueous solution of copper, and this is copper. Will electron flow from copper to copper solution? Will it reduce? We don't know. You just have to wait and see the reaction. If it is, and then you'll have to try. It's just trying and error until you understand. The purpose of this is just to give you an idea on whether there will be reduction of the ion in the solution, reduction of ion in the solution. You will go back and forth until you are confident on reduction oxidation. At the bottom here there is next. This is just giving you an idea. You can practice this more and more until you get it. But for the data sheet, let me just get to the data sheet on how you will. This is just explaining what I went through on that. On the data sheet, where they talk about constructing a cell. You see the voltammeter there. Let me just see if it's gonna allow me this. You have the solution on solution right here. You have the electrodes right here, 1 molar. And the red one, it is what? It is the cathode. This is the anode, so that when you calculate the standard cell potential, you should be able to get that. So in our data sheet, let's see what they are talking about right here. You need to construct a cell. You need to construct a cell which I need to get this out of my way. You need to construct a cell consisting of zinc and silver, consisting of zinc and silver. Here is zinc and zinc, but how are you going to construct one for zinc and zinc? You can pick any, and record. On the data sheet, you are required to, all right? On the data sheet, you are required to construct one for zinc, but here, I'm just showing you how you're going to construct one. You can check and see how that works. It doesn't work, that means not going to work. These are the electrodes. This works as solvent. This is for diluting in part P, but you need to construct one for zinc and silver. So this is one of the half. If I want to get to, say, zinc and copper like that, that means you are reducing copper. You need to change the solution right here, okay? You need to change the solution on the cell. You need to change the solution on the cell. So initially, if the solution is different, you'll just have to drag. I think, since my right here, you are reducing. If this is the anode, and then you select what? What is happening? It's oxidation we are losing. Let's see. Zinc, anode. So that means reduction. Anode. Oxidation, this was based on this right here. It tells you what is going on. So this is cathode. Yeah, just go back and forth for this type of setup. So for your case, you'll have to do the reaction for zinc and silver, and you'll take a picture. You'll take a picture of what? You'll take a picture of your cell and put it in the, paste it on the data sheet. You're gonna paste it on the data sheet. Make sure you take a picture of what you have right here. This is where you put in there. Okay. Any question on that? Any question? Any question? So you'll do this. If you want to do any, any of, you're gonna check this and check. Let's say if I want to construct for copper and zinc. So for copper, copper is anode, which is positively charged. I'll take the, doesn't really matter where you put. And this will act as the soul bridge. You see, the highlighted one tells you where you want to put it. I'm just gonna put right there. And zinc sulfate solution, I'm just gonna put right there. And put the paper right there. So, from the standard, I recommend that you can print it or have it elsewhere. From the standard cell potential I showed you earlier on, you can use that table to indicate which one is anode, which one is cathode. We saw that zinc was above copper on that table, which means zinc is anode, which is negatively charged. And I will grab the negative. You have to know. You see where it is highlighted as blue? I'm just gonna put it where it is blue right there. Don't put it right, no. Where it is highlighted, just right there. That's correct. And then now, to immerse in the electrode, I need not silver, no. Remember, use the same electrode. So I'm just gonna put the same electrode. Zinc solution is close with that. Since copper was below zinc on that standard electrode, I know it is my cathode. This is where reduction takes place. This is where we lose electrons, negatively charged, positively charged. So I'm gonna grab the electrode copper right here. I want you to look at the potential right here, because you're gonna be recording the potential on the data sheet. I'm just gonna grab this. Look at what's going to happen. You see how it's recording? This is what it is, 1.1. I guess I made a mistake in my example on the whiteboard. It should be 1.1. That's how you construct on the simulation. Well, the purpose of this water here, it will call for diluting. When we get to non-standard state, you will be diluting. If you took note of metal here, these are the metals you will be working with their respective solution right here. The data sheet talks about metal X, so you have to specify your metal X in your data sheet, that this is my metal X, and write the what? Write the half reaction taking place in the anode, taking place in the anode. At some point, you will do what? Dilute the solution. The purpose of that is to dilute. I didn't mean to. This, I don't need that. The purpose of this is to dilute the solution. Now you're going to dilute. Watch what will happen to the voltage reading if I just put the water there. That means I'm diluting the solution. You see, saying dilute, and the voltage has changed. As the voltage has changed. So let me just pull the data sheet. This is the data sheet which you will construct for this using the simulation the way I just did. The anode, the cathode, take a picture and then place it right there. Okay, and the other one is constructing using this, the way we did. Take a picture of that. When we say metal X, I have what is the balance, have cell reaction that corresponds to reduction. You know what reduction is. I showed you earlier on in my whiteboard, reduction. So you have to write the equation, and when they say balance, sometimes you may transfer one electron, sometimes you may transfer two electrons. You got to balance the electron and then you put it in there. I think you're gonna do twice for that. Same thing for this. Twice, there is metal 1, metal 2. Now, here is the measured value. What is measured? Measured is what you see on, what you will see once you construct your data from what? From this. That's the way you did. You just put the solution, solve it, what do you hear? This is the measured. And then the calculated one will be using the standard right here. You'll have to calculate. This is the same thing I showed you earlier on. You're gonna calculate using these values, using the standard, and compare the values on the right here, calculated. I want to show you the calculated one for half cell. So you're just gonna calculate right here and produce you may attach your calculation, all right? And this is the measured one using the simulation online. You'll do for only two methods, validation 1 and validation 2. You're gonna do for 2 methods. And then at non-standard state, you see here, non-standard state, you will have to, if you go back to the original data sheet, right here, the original page, this is what I wanted to show you, the last part, right here. Non-standard state. You can practice right here, non-standard state. Oh, it's gonna load. That's what they meant. You will see that non-standard state, and then you do the same thing. You do the same thing. This is non-standard state. It's just gonna give you a hint. You know this is the cell. You know where the reduction is. All right. And read that literature. You'll do the same thing for non-standard state. You'll construct a cell. That's the way we did. All right. It's gonna explain to you what to do with this same thing you did before and answer the question which follows, all right? You will dilute your solution, reaction 1, reaction 2, and see how the voltage will change. You see how the voltage will change. This is where you talk about diluting the solution. That will give you information you need to answer on question 4. Question 4. All right. If you look at question 4, it tells you. Let's see. Show you question 4 right here. You're gonna practice dilute zinc. So this means we have a thin electrode, all right, and reaction 2, reaction 1, reaction 2, we have, there is copper and zinc, and I see copper is being reduced. Zinc here, this is the anode. So how do you construct this? For zinc, and you see the electrode potential, standard potential right here is 0.48. So what will that be when we construct our value? Zinc, if I do zinc, so that means thin. Sorry, I'm gonna put thin right there. And I think it was copper right here. And I'm gonna use the same electrode right here. I'm gonna use the same electrode for copper right here. And then anode was thin, right? Losing electron. Let's see. I could be wrong. If it doesn't work, yeah, it doesn't work, right? No, I haven't put the what? The solve break. Let's see. Complete the solve break. Yeah, that is what it is. That is what it is. 0.48. Talk about diluting. I don't know which one you are diluting. I think it was this one, and what happened to that. And then you explained that diluting is just scrapping water here and then just putting it. And you put it in there. You can add You can use extra sheet of paper for your calculation, and that is, I think that is pretty much straightforward. This is at non-standard state. This is where Nast equation, behind the scene, Nast equation is playing a role here, in the sense that it is no longer 1 molar. You see, this is 1 molar. This is no longer 1 molar, and Nast equation is used in calculating the, cell potential for the galvanic cell. There are a lot of information I didn't go through in this simulation, which will help you also in lecture part if you are taking the course and the text doesn't really explain much. Use this also as a resource. It's a useful resource. With that, I want to end our discussion today. If you have any question, please send me an email. I know you may have issues with the Adobe Flash. It might not play on your straight up on your computer. Please send me an email, and I'll try to post on Canvas. That way you may go through. Other than that, is there any question? Any question? Let me just minimize this if there is any question. Yes, Cynthia, you have 2 questions. Let me just see here if I can, Cynthia. What is the question, Cynthia?
Okay, so can you hear me?
Yes.
Okay, so my first question is, for metal X, are we trying to find what X is?
Yeah, you can pick any metal right there, because we have 2 metals right there. Metal X, you can say zinc or copper. Like if you look on here, we have more than 1, 2, 3, 4, 5. We have more than 2 actually. So you don't need to do all of them.
Okay, so we just choose one to do.
Yes, and that's why they say X. And somebody can use a different one. Somebody can use a different one. And
okay, and
that will work.
My other question is about the post lab.
Yes.
I was working on number 7, and I couldn't find, figure out what in is.
What?
I couldn't figure out what in is, because I see where
let me just pull number 7, and that way I will, really look at, maybe there was some missing information, or,
Well, I mean, because I could find what was oxidizing, but I couldn't find what was reducing.
Let me just look at that. Let me just look at post lab, right?
Yes.
Okay. I'm gonna show you that real quick right now. Sometimes can be tricky. Post lab right here. Let's just look at that. Number 7, correct?
Yes.
All right. Let's just see that. All right. Number 7 here. It's talking about there is an equation here. E cell. All right. Is 1.88. Find the E. This means at non-standard state, correct?
Yes.
And you're wondering, where am I gonna get the N, correct?
Yes, that's the only thing I'm missing.
Yes. This is I can say this is pretty straightforward, in the sense that you can use. If you look at aluminum, what does this tell you? It has lost how many electrons?
It lost 3.
And if I have 3 chloride ions, and each chloride is Cl, if I have Cl negative, it means 1 electron has been gained. Just Cl is chlorine neutral, correct? And then Cl negative, super negative, it means you have just gained 1 electron. But if I have 3 of them, that means how many electrons do we have here?
3.
So does that give you an idea?
Yes. So just to clarify, I was looking at the solid, the silver chloride. So in that instance, chloride would be 0. Is that correct? Because I'm trying.
The
Because I
chloride.
see it's -3 also.
Yeah. This should be aqueous because we are reducing it to solid. This should be aqueous, so that will change.
Oh, okay.
Yeah. I see your question. That is valid. Like that. If I think that will change now.
So now it would be. Well, wouldn't it
Because
still be
we are
-3?
reducing silver to silver solid, and this one solid to aqueous.
Yes, but for the chloride part, that's where I'm messed up.
The question is what again?
I'm trying to find what's reducing.
Oh, what is reducing? Okay, reducing agent, right?
Yes, because I don't see any change in the number of electrons that are present in the reactant versus when it's on the product side. I only see that for aluminum.
Sometimes the chloride is just to balance the charges, but in these two things, electrons are moving actually from, because chloride is negative, right? So this will be, in this case, I see this is considered as reducing, what is being reduced here is silver ion. And what is...
Oh, okay. Okay, I see what you're saying. So that would be going to 0, from +1 to 0.
Yeah.
Okay. All right. Thank you.
All right. So if there's no other question, I will stop sharing my screen, and I expect to see your work probably this Friday. Thank you. Be safe. If you have any question, please send me an email and I'll respond. The class is dismissed. Be safe.